Hi everyone. Welcome back to Dave's Math channel. This is my third video on practical math, and today I'm going to talk about a problem probably most of you have heard before. It's called the birthday paradox, and there's a lot of literature about this problem on the web, and like I said, you've probably heard of this problem, but in case you haven't, here's the paradox. So the question, let's just start with a simple question. Imagine you go to a party where there's say I don't know how many people at the party, but you want to know how big a party that party needs to be in order for it to be more likely than not that two people at the party have the same birthday. You might think that's pretty unlikely for a small group. And most people think it's around, since there's 365 days in a year, it seems kind of intuitive that maybe you should have close to 365 people at the party in order to ensure that two people have the same birthday. Actually, that's not true at all. And the reason it's called a paradox is because the result is very surprising to most people. It turns out that the minimum number of people you need to have at the party in order to ensure that there's at least a 50% chance that two people will share the same birthday is only 23. If you have a party with 23 or more people, then it's more likely than not that two people at the party have the same birthday. That seems very counterintuitive. Why only 23? I mean, that seems like a pretty rare coincidence for two people at a party have the same birthday. Well, the reason it seems like a paradox is because most people think about this problem in the wrong way. Maybe they're thinking about who shares a birthday with you. It is pretty likely that unlikely that if you go to a party, you're going to meet someone at the party that has the same birthday as you. For that, you probably need about 180 people or more because you have to have someone at the party matching your birthday, and for each person at the party, there's only a 1 in 365 chance of that happening. So it does make sense that there should be close to the number of days in the year in order for that to happen. But what you really need to realize here, they don't have to share a birthday with you. They just have to share a birthday with someone else. And so the thing you want to be looking at is not the number of people at the party, but the number of pairs of people at the party. And it turns out that if you have a party with 23 people, if you want to count the number of pairs of people at the party, that's actually 23 choose 2, which is 253. There are 253 pairs of people in a party with 23 people. And it's just enough to have a pair of people at the party with the same birthday. So since there's 253 pairs, then you would think that that makes it a lot more likely. And it turns out that it is. I mean, this is a rough estimate, but if you take I mean, just imagine that you have pick two people at random at the party. It doesn't matter who. And then what's the chance that they share a birthday? 1 in 365, right? So the chance that they don't share a birthday is 364 out of 365. But that's for any given pair. But there's 253 pairs, which means that the probability of there being a pair of people at the party that I mean, the probability that no pair of people at the party has the same birthday, then there are no two people with the same birthday. There's approximately 364 of 365 to the 253rd power because you're looking at 253 pairs. This is, of course, assuming that the probabilities are all independent. If they were all independent, you would get this exact figure, which turns out to be 0.4995 approximately. So that's why you need 23 people at your party. But this isn't the exact answer. This is just an approximate answer. It's pretty close to the right answer. But to get the real exact answer, you have to do a little bit more analysis here. So the probability that let's let Pn be the probability at a party with n people that at least two people at the party share a birthday. Well, that's just 1 minus the probability that everybody has a different birthday. And to do that, I mean, imagine you're just going through people at the party. I mean, say you're the first guest, then there's nobody you could share a birthday with because you're by yourself. But then let's consider the second guest. What's the probability that they share a birthday with you? 364 over 365. And then you add a third person to the party. What's the probability that the third person shares a birthday with either you or the second person? Well, now it's 363 over 365. And you keep going. And by the time you get to the nth guess, the probability that they share a birthday with anybody else at the party is around 364 minus n over 365. So you have to multiply all these factors together. And you have to subtract that from 1 because this quantity in the parentheses is the probability that no two people at the party share the same birthday. So the probability that there are two or more with the same birthday is just 1 minus that. Well, you can calculate this. It's a pretty horrendous calculation, but that's what computers are for. And if you simplify this expression, here's what you get. You get 1 minus n factorial. That's just uh, uh, and in this case 23, if n is 23, 23 times 22 times 21, all the way down to 1. That's a very big number. And then you divide that by 365 at the end. That's another really big number. It's bigger than n factorial, it turns out, for all n. And then you multiply that by 365, choose n. And it turns out that this is an exact formula for the probability that two people at the party share a birthday, if you have n people at the party. And it turns out that 23 is the smallest value of n. That gives you a probability greater than 50%. Here's a graph. This is a nice graph. And you can kind of see what's going on with this graph. I mean, I think this is a very interesting graph because, I mean, first of all, you see how this thing increases. I mean, it starts out very, very small. If you just have a few people at the party, there's almost zero chance that two people share a birthday. But it grows kind of quadratically. You notice this thing looks sort of like a parabola for a while. It's growing like the square of the number of people, which kind of makes sense because the number of pairs of people at the party, uh, uh, grows n choose 2. That is n times n minus 1 over 2, which is roughly n squared over 2. So it grows like the square of n for a while. And then by the time you get up to n equals 23, you get 253 pairs of people. And if you calculate the probability, you get a little bit more than 50%. Remember, this probability is not just n choose 2. It's 1 minus 300. It's roughly 300, 1 minus 364 over 365 to the quantity n choose 2. That's roughly what this graph is showing you. And since the number of pairs of people grows very fast, it grows like the square of the number of people at the party. Then by the time you get up to, I mean, by the time you get up to like 40 people at the party, it's already about a 90% chance that two people share a birthday. This gets very, very close to 1 very fast. By the time you're up to 60 people, it's probably around 99%. And by the time you're up to like 100 people, it's probably 0.99999. I mean, you don't have to get that many people at your party to ensure that it's almost certain that two people at the party share a birthday, and probably even more than two. At some point, you're going to get it'll be more likely than not that three people share a birthday. I think I actually did this problem a few months ago. I think you only need about 70 people at the party to ensure that at least three people at the party share a birthday. And it is a kind of counterintuitive result, but it's one where you just have to think a little bit about what's going on. And then once I think you understand what's going on, that's really the number of pairs of people at the party rather than the number of people at the party that matters, then I think it should make a lot more sense. Anyway, that's my explanation of the birthday paradox. I hope you enjoyed it. Thank you for watching. Long live math, and I'll see you next time.